Hello everyone and welcome to this class dedicated to ceramics that is given in the frame of the course Materials and Their Properties from the Federal University of ABC in Brazil, and I am Professor Mathilde Champeau. So today we are going to introduce some applications of ceramics, and I'm sure you know some of them, and the classifications that are possible for ceramics. Then we will introduce their composition and the kinds of chemical bondings we find in these materials. We will learn how to find the crystal structure of ionic ceramics, and finally we will introduce silicate ceramics. So let's have a look to this different class of materials. So first of all, we introduce metals and then polymers, and now we are going to present ceramics. So let's remember, metals have high density, a medium to high melting point, they have a medium to high elastic modulus, they are reactive and ductile. The polymers have a very low density, a low melting point, low elastic modulus. They are very reactive, and we find both ductile and brittle polymers. And what about ceramics? So ceramics have a low density. They have a high melting point, a very high elastic modulus. They are unreactive and brittle. So focusing on ceramics, what are the application of these kind of materials? So I'm sure you have already seen some of them. For example, clay-based ceramics are used for brick and for this kind of dishes. We find ceramic in whitewares, so either toilets or your cup of coffee, and some of the tableware. They are used for creating abrasive material, in insulator for electric applications, and also refractory ceramics are used. So here you can see that this ceramic is used in that case in this pot, okay, to create these recipients, since it can sustain very high temperature without any modification. So it is used to create this recipient to melt metals, for example. Okay, so we also find cement or ceramics, plaster also. Ceramics are also used for creating dental implants, as this one, as you can see, ceramic glass and silica glass. So the range of application are various, and we find these ceramics, as you can see, both in civil engineering applications, in aerospatial, in for electrical applications, in the industry of metal transformation, and for some applications that are much more decorative also. So ceramics, the word is of Greek origin. So ceramics comes from keramos, which means burnt solid, because as we will see, heat is used in order to be able to create this kind of material. So they are submitted to high temperature. So they have been used before Christ, first as clay artifacts or earthenware, and then as pottery. As you can see, this picture is an example of use of ceramic for food storage and vessel. Then in China, porcelain has been created. And then in the 18th century, porcelain has been more explored. There have been the development of ceramic processes that enable the more diverse shapes of ceramic products. In the 19th century, because of mechanization, the development of optical microscopy, the understanding of ceramics have been improved. And finally, in the 20th century, since we had development of new characterization techniques such as X-ray, fluorescence, X-ray diffraction, electron microscopy. So we have been able to understand better the composition of these ceramics, and also the range of application increased, and there have been the development of high-tech ceramics. So this very wide range of kind of ceramics lead to the need of classification systems of these ceramic materials. So we find basically two classification systems. We have the first one that is based on application of these materials, and the other one based on composition. So let's have a look to the classification that is based on ceramic applications. So as you can see on this graph, that have been found in the literature. So we have traditional ceramics and advanced ceramics. So basically traditional ceramics are those that compose whitewares, structural clay products, brick and tile, abrasive, refractories, and cement. Whereas advanced ceramics, as you can see in this diagram, are either functional ceramics, that means they have functional properties such as a specific electronic property. For example, we find a capacitor dielectric, piezoelectric ceramics, magnetic ceramics, optical ceramics, conductive ceramics. So as you can see, the functionality, the specific property of ceramics have been developed, and so we classify such kind of ceramics into the class of functional ceramics. We also find structural ceramics such as nuclear ceramics, bioceramics for biomedical application, tribological ceramics, which means that they are wear resistant, and finally automotive ceramics. Okay, so these two main blocks, traditional ceramics and advanced ceramics. And before going to the next slide, here you have the logo of the Associação Brasileira de Cerâmica, which is an association that gathers specialists in ceramics in Brazil in order to organize conferences, to share their knowledge, the advancement of the industry in this area. And so we have one in metals, one in polymers, and this is the one in the area of ceramics. So continuing on the classification, traditional ceramics versus advanced ceramics. So traditional ceramics may have one or more of the following characteristics. They are produced predominantly from natural raw materials, as we will study. They have a coarse microstructure, so large particle, large grains, and less control of chemical and phase purity than advanced ceramics. On the contrary, advanced ceramics are designed for a specific purpose, as we saw. They have been developed much more recently, and they are produced predominantly from synthetic raw materials. They have a fine microstructure, so with micrometric or submicrometric grains, and a higher control of chemical and phase purity than traditional ceramics. So now focusing on the definition and the composition of these ceramics. So ceramic materials are solid compounds formed by the application of heat, sometimes heat and pressure, which can be constituted by metallic, non-metallic, or intermediate elements. So they are either crystalline or amorphous, in the same way that we saw for other kind of class of materials. And the chemical bonding in ceramics are either pure ionic character or ionic covalent character, like an intermediate character, and some of them are covalent. So what about the composition? They are composed of at least two elements, so metallic and non-metallic elements. So in the case of ionic ceramic, we find such kind of element, or this combination of this kind of elements leads to ionic ceramics. They are composed of ions that comes from metallic elements. So the metallic element will form the cation in our ionic ceramic. And the other element will be a non-metallic element like oxygen, nitrogen, chloride. These non-metallic elements, due to their electron structure, will tend to gain the electron that the metallic element will give to them. Okay, so in this with such kind of composition, metallic, non-metallic elements, creation of cations and anions, and formation of ionic ceramics. So here you have some example of ionic ceramics. But we also find ceramic composed of only non-metallic and intermediate inorganic compounds, which is the case of silicates that are composed basically of silicon and oxygen. And in that case, these elements are bounded together by covalent bonding. So in the case of fluoride, which is composed of one atom of calcium and two atoms of fluorine, so calcium comes from metal, the metal part of this periodic table, whereas fluorine is an halogen element. And so, as we will see, fluoride is an ionic ceramic. In the case of silicon, which is composed of silicium and oxygen, both of these elements are from are intermediate elements in non-metal, and so it leads to a covalent ceramic. So here is to remember the different class of elements in this periodic table. So the metals, intermediate elements, and non-metal elements. And let's remember that in the second class, we describe the evolution of electronegativity in the periodic table. So it's the electronegativity increase from in that direction. So I will draw it, it will be easier. So it's increased from here to that direction. So I hope you can see. So in that direction. Okay. So just to remember, because it will be useful in the next slide. So I'm going to remove it. Okay, so let's remember the chemical bonds. We saw that in the second class we saw ionic and covalent bonds, and we explained their characteristics. So the ionic bonding involves an electron transfer from one atom to another. So we presented the case of sodium that will give an electron to chlorine in order to create this salt. Okay, they are non-directional, so the magnitude of the bond is equal in all directions around the ion. And we already introduced a high electronegativity difference between the elements. So in the case of sodium, the electronegativity is 0.9. In the case of chloride, it's 3.0. So if we calculate the electronegativity difference, it gives 2.1, and we just said that it is related to ionic character, and now we are going to explain a little bit better this relationship between ionic character and this electronegativity. But we had already explained that in the case of ionic bonding, we have a high electronegativity difference, and the ionic bond is due to the electrostatic or Coulombic attractions between two ions of different electrical charges. So it is the case in this kind of ceramics. And here in this example of sodium chloride, we have Coulombic attraction between the cation made of sodium and the chloride coming from that is the anion. Okay. And the Coulombic forces change with the square of the inverse of the interatomic distance. So, as we said, ionic bonding will be found in compounds that are composed of both metallic and non-metallic elements. And then we also introduced a covalent bonding. So covalent bonding involves the sharing of electrons between adjacent atoms. A covalent bond is directional. It is between specific atoms and exists only in the direction between the two atoms. So in the case of covalent bonding, we have two atoms with lower electronegativity difference between these elements, will tend to form a covalent bonding. So during the second lesson, we gave the example of methane. So we have one atom of carbon with 4 atoms of hydrogen, and each hydrogen will share 1 electron with the carbon atoms to create a covalent bond. But this kind of molecule is not part of a ceramic classification. So here we will introduce in that class silicates that are composed of silicon and oxygen, and silicon and oxygen have a lower electronegativity difference than in the case of sodium chloride, and they form covalent bonding. So let's remember covalent bonding found in compounds that are composed of non-metallic elements, found on the right side of the periodic table, as we already explained. So let's go ahead. Many ceramics exhibit a combination of ionic and covalent bonding, and the degree of ionic character is dependent on the difference of electronegativities between the two atoms. So there is this equation to calculate the percent ionic character in a ceramic. And you can see that we can calculate it knowing the electronegativities of the two atoms, A and B. And as a general rule, we will say that if the difference of electronegativity between the two atoms are higher than 1.7, we have a predominantly ionic character. And if this difference of electronegativity is lower than 1.7, predominantly covalent character. Okay, and this is very important because in fact it will explain the properties such as mechanical properties and thermal properties of these ceramics. So that's why it's important to have to know what is the character, ionic or covalent, of the bonding in a ceramic. So here you have different ceramic materials that are listed in this table with the percent ionic character calculated for all of them. So as you see, the fluorite has a high percent ionic character, and silica a much lower one, so 50% ionic character, 50% covalent character. Okay, and we find, for example, zinc sulfide that is much more covalent character. And here in this graph, it shows the evolution as a ionic character, a fractional ionic character, or if you multiply by 100, it will give the percent ionic character as a function of the difference in electronegativity. And you can see that it's increased the fractional ionic character according to this graph and according to this equation is increasing with the difference in electronegativity. Okay, so now let's focus on ionic ceramics. So the ceramic material formed by ionic bond. So in that case, we will have cations and anions in these materials. So in order to know which kind of crystals are formed by these ceramics, we have to take into account two characteristics of the ions. First of all, the magnitude of the electrical charge on each ions and the relative sizes of the cations and anions. So the first rule that we will have to take into account to be able to determine the crystalline structure of a ceramic is the crystal that must be electrically neutral. So let's take the example once again of fluoride. So if we write down the electron configuration of calcium, and if you write down the electronic configuration of fluorine, so we will see that calcium has 2 valence electrons, and fluorine has 7 valence electrons. So in order to reach the stable electron configuration, calcium will have the tendency to give its 2 valence electron to fluorine. And fluorine, in order to reach the stable electron configuration, will tend to gain 1 electron. So in order to have a material that is electrically neutral, we need to have 2 fluorine for 1 calcium atom. Okay, so how we will write down the composition of the ceramic? So we will write that we have 1 calcium, so calcium, a symbol of calcium, and 2 atoms of fluorine, so the symbol of fluorine, F, with unsubscribed number 2. Okay, and so that's why when you will read books and articles and works about ceramics, the composition of the ceramics will be always given in this way. And so the subscribed letter will give you the number of such an atom, of each atom, in fact, in the composition of the ceramics. And so the overall point of this first rule is that the crystal must be electrically neutral. Okay. So now let's go to the second rule, which deals with the space occupation by ions. So when we talked about metals and crystal structure of metals, we explained that we can find different arrangements of the atoms, FCC, BCC, hexagonal, and so on. So now we are going to understand, in the case of ceramics, we have anion and cation, and we need to understand how they organize each other. What are the rules, okay, to follow for the space occupation by ions in a unit cell? So the rule is the following: stable ceramic crystal structures are formed when the anions surrounding a cation are all in contact with that cation. Okay, so and the second rule is to maximize the number of nearest oppositely charged neighbors. In this figure are represented three configurations, three possible configurations. In this representation, we have the anions that are represented as big circles. Why as big circles, bigger than anions? Because in fact, since we have anions that are accepting more electrons and cation giving up electrons when ionized, so cations are ordinarily smaller than an ion. So that's why we represent the cation smaller than the anion. And in these three representations, the first two cases respect this rule to get anions directly in contact with cations. So these two representations will be stable, whereas the last one, we don't have a close contact between the anions and the cation, so it is an unstable configuration. So the space occupation by ions should respect this second rule, okay? And so the radii of anions and cations and the organization of the anions around the cations will be very important. And so in order to know what will be this organization in a more precise definition, so we should first have a look to the coordination number, which describes the number of anions nearest neighbor for a cation. So this is a description of the coordination number, the definition of coordination number in case of ceramics, ionic ceramics. So first of all, how to determine the coordination number? First, we should calculate the ratio between the radius of the cation and the radius of the anion. Okay, because it is dependent, this coordination number is dependent on the size and the relative sizes of cation and anion. So first, we determine this ratio of the radius of cation divided by radius of anion. And depending on the specific value of this ratio, so we should have a look to this table that is presented on this slide. That will give us the coordination number. So for example, for a cation and anion radius ratio lower than 0.155, so the coordination number is 2. So what is the coordination geometry? It is represented on the right column of this table. Okay, so this is a way we determine the coordination number and the coordination geometry. So once again, we calculate the ratio between the radius of the cation and the radius of the anion. Depending on the value, as you can see, this will give us the coordination number, and this coordination number will give us the coordination geometry. So let's consider the second row. Indicate that this ratio is between 0.155 and 0.225. So the coordination number is 3. So coordination geometry is trigonal. So each cation, small cation in blue, is surrounded by 3 anions in orange in the form of a planar equilateral triangle with the cation in the center. So you have a definition of this geometry. Let's take the example of a ratio of the cation radius, and so right here in this kind of situation where you have a ratio between 0.414 and 0.732, coordination number 6, coordination geometry is octahedral. So the cation is in the center of octahedron. So here is a representation, 3D representation of octahedron. Okay, so once we have the coordination geometry, we should find a way of finding the specific localization of the anions and cations in the unit cell. So depending, following the first rule that tell us how many, that tell us the composition, the chemical composition of the ceramic, and verifying the second rule that gives us the space occupation by ions. So we find what is the unit cell and where are placed the anions and cations. So here are three very common example and more simple example of ceramic that are composed of the same amount of cations and same amount of anion. So a kind of crystal structures that are AX types, same number of A, same number of X. Okay, so crystalline structure in ionic ceramics obeys the structures described by the Bravais lattices. So anions, because they are bigger, occupy position of the lattice, whereas cations, because they are smaller, occupy interstitial positions. So as you can see on this example, you have the anions that are presented in green, and the cations that occupy interstitial positions that are represented are as smaller blue points. And due to the fact that you have a ceramic with different kind of structures, different kind of stoichiometry, and due to this calculation or this second rule that gives us the coordination number and the geometry coordination, so we have different crystal structures in ceramics. And for example, we will have to find for FCC a structure formed by anions the different interstitial sites. So we have octahedral sites that are represented right here in this figure. And so the circle indicated by O, or an empty circle, represents the centers of the octahedral interstices. And so this will be the possible position of the cations in case they are placed in octahedral sites. So in the case, let's go back to this, this table. In the case, we found that the coordination number is 6, and so we have the necessity to find the octahedral interstices. Okay, so here you have the representation of the position of the octahedral interstices. But we also have in this FCC structure formed by anion, the tetrahedral sites represented right here. So if you compare the octahedral sites and tetrahedral sites, of course, they are distinct. So previously, in the case of metals, we defined how to calculate the density of a metal. So let's remember we presented this equation where we have the number of atoms in the unit cell, the atomic weight of this atom, the volume of the unit cell, and the Avogadro number. So it was quite simple in the case of pure metals. Now we are dealing with ceramics that are composed of more than one atom. So what is the equation to calculate density? So here we should consider the number of formula units within the unit cell. So for example, in the case of barium titanate that is represented right here, okay, on the bottom of the slide, you have the chemical formula of barium titanate. So how many of these formula is present within a unit cell? So we need succeed to draw this unit cell, and then we calculate the number of this formula. Then we calculate the sum of the atomic weight of all cations. So in the case of barium titanate, what are the cations? We have only barium cation and titanium cation, so we should consider it, and we will consider the sum of the atomic weight of all anions in the formula unit. So in that case, we have the oxygen anions, 3 oxygen anions in this formula. Then we divide it by the volume of the unit cell and the Avogadro number in the same ways that we did for metals. Okay, in that applying this equation, we are able to know the density of the ceramic. So considering or applying the 2 rules that we saw to determine crystalline structure in ionic ceramics, let's first consider the crystal structure that are from the AX type, which means same number of cations, same number of anion in the chemical formula. So as an exercise, you can make the step-by-step in order to determine the crystalline structure of these ceramics. So let's remember, first of all, you will find the ratio, the radius of the cation and the radius of the anion in the literature. Then you will calculate this ratio between the radius of the cation and the one of anion. Then you will determine the coordination number looking at the table we introduced, then the coordination geometry, and after that, finding the specific interstitial geometrical interstices in the unit cell, you will be able to place your cations, okay? And so you will have the crystal structure. And so if you do so, you will see that for sodium chloride, you will have such kind of unit structure. So in this case, we can describe it as a FCC arrangement of anions with 1 cation situated at the cube center of one of the center of each of the 12 cube edges. Okay, so in that case, you have a chlorine, which is an ion that is placed in this FCC structure, and you have sodium cations that are placed in the middle, in the center, okay, of each edge, sorry, of this cube, and one more is placed in the center right here of the unit cell. In the case of cesium chloride, so the structure is much simpler. So chloride is placed as each corner of this BCC crystal structure, and one cation of cesium is placed at the center of this BCC crystal structure. Oops. In the case of a zinc blend or zinc sulfide, if you apply the rules that we introduced, you will end up with such kind of structure. So all corners and face positions of the cubic cell are occupied by the sulfide atoms, while the zinc atoms fill interior tetrahedral positions. So here in red is represented a tetrahedron, and so you find the zinc at the center of this tetrahedron, okay? And so if you reverse this position, if you place the zinc or if you dislocate, translate this unit cell a little bit, so you will find that the zinc and sulfide atom positions can be reversed and you find the same unit cell, the same structure. So here you have some application of a zinc blend material, so in military area, in solar cells panel, in medical diagnosis, in monitoring, and so on. So you have an idea of where this material is used. Now let's consider the cases in which the number of anions and the number of cations are not equal in the chemical formula. So we will write this kind of composition in a general way with A, M, X, P, and M is not equal to P. It is the case of fluoride, where we have 2 fluoride for 1 calcium. So applying the second rules, you will find that the ratio, ready ratio will be about 0.8. And looking to the table we presented, the coordination number is 8, which means that you have a cubic geometry. So you have, like the case of cesium chloride structure, you will have a similar structure where the fluorine anion will be placed at the corner of a cubic cell, and you will have the cation, calcium cation, at the center of this cubic cell. If you apply, if you consider this structure, you will find that this structure does not allow to respect the chemical formula. And so you won't have an electrically neutral unit cell. So in order to get electrically neutral unit cell, in fact, you will have to represent this situation. It's like you have 8 unit cells, okay, of fluorine, and only 4 of these unit cells have a calcium atoms, a calcium cation at the center. Okay, if you make the calculation of the positive charges and negative charges in the unit cell that is presented right here, you will see that this structure respects the first rule, electrically neutral, and the second rule that we introduced, to have calcium in a cubic in the cubic geometry. Okay, and so that's why here we are introducing a more complex unit cell than the one that we studied up to now. And so this material is used because it is a very hard material, and it is used to produce durable and resistant materials in some very resistant window in some equipment, for example. So now let's go in a much complex situation where you do not have anymore only one kind of anion, one kind of cation, but you begin to have 3 kind of ions in your crystal structure, which is a kind of peroxide crystal structure, which is ABX3, like the one that we introduced, the barium titanate. And so in that case, we need to find the right place for each of these ions. And so here is the representation of the unit cell of perovskite crystal structure. As you can see, it's become a little bit more complex. Okay, so we are not going to focus on such kind of material, but it's for you to know that applying the first rule, the second rule, so now we are able to go to more complex unit cell. Finally, let's talk about silicate ceramics that are an example of covalent ceramics. And so if we used the concept of unit cell to describe ionic ceramics, what about the case of covalent ceramics, and here particularly of silicate ceramics? So first of all, silicate ceramics are basically composed of two elements that are the most abundant elements in Earth, that are silicon and oxygen. And instead of using a unit cell to describe the structure and the organization of atoms in silicate, we are going to use this tetrahedron structure, which is a basic building unit of silicate. So let's have a look. If we consider silicon and oxygen and their difference of electronegativity, let's remember that we will find that they have a covalent character. And so they form a covalent character bonding, and what is the arrangement of these atoms that enable to respect the directional requirement of the covalent band and the ratio between the radii of between silicon and oxygen. And so in fact it justifies this tetrahedron unit. So you have this tetrahedron formed by oxygen, four oxygen anion at each corner, and one silicon cation at the center of this tetrahedron. And so you have a unit cell that is negatively charged with four negative charges. And the silicate ceramics, in fact, will be composed of different combination of these tetrahedron units into 1, 2, or 3D structures. So the most simple silicate material is silicon dioxide, or silica. Okay, so 2 atoms of oxygen for 1 of silicon. It is a 3-dimensional network that is generated when every corner oxygen atom is shared by adjacent tetrahedra. So as you can see, maybe it will be this oxygen atom that is part of this tetrahedron is also shared with this tetrahedron. Okay, so in that case, you have a material that is electrically neutral due to the fact that these oxygen are shared with 2 tetrahedrons. And so in these circumstances, if you calculate the ratio between silicon and oxygen, so you will end up with this chemical formula. Okay, so that's why silica is represented with this chemical formula: 1 atom of silicon for 2 of oxygen. And it is the most simple silicate material, as we said. So silica is found in crystalline form and amorphous form. So dealing with crystalline structure, we find 3 polymorphic forms of silica, which are cristobalite, tridiamide, and fused quartz. All of them have present different arrangement of tetrahedrons. But in any case, we find a very compact network, which is responsible for the low density of crystalline silica, even in the crystalline form. And on the other side, we have amorphous form of silica, which is also known as glass. In this situation, we have disorder of this tetrahedron. And so in many situations, in order to form this glass, in order to form this irregular structure, we used to add small quantity of oxides, for example, to obtain or to fabricate the windows and other containers that we find in our everyday life, that we call glass. In fact, we add a small amount of other oxides, such as carbon oxide. Their cations are incorporated into the tetrahedron network, and it modifies it, so it hinders the ordering of this silica network, as you can see on this scheme. And other kind of oxides, like titanium oxide, will enable to substitute silicon and to stabilize the glass that is formed, okay? And the addition of this small amount of oxide have an effect on the melting temperature, since it is going to lowering the melting temperature and will decrease also the viscosity of the glass, and it will be easier to form such kind of glass at low temperature. So this kind of composition are called soda coal or soda glass in the jargon. Then we have silicates that have a much more complex organization. So as you can see in this representation, it is to illustrate the kind of the case of clays, where we have tetrahedral sheets, octahedral sheets, and the sequence of this kind of different sheet, and some interlayer gallery in which we find cations. And so you can see that if we find again these patterns of a silica tetrahedron, the overall structure is much more complicated. So now you know the elemental composition of ceramics, you know how to determine the ionic covalent character of a chemical bond in ceramics. We described the rules to determine the crystal structure in simple ionic ceramics. And finally, we studied a little bit silicates, either crystalline and amorphous. So I hope that you have learned a lot about ceramics and composition of ceramics. So if you have any question, you can write me an email at this email address. Bye-bye.